Thank you. Thank you everyone for coming. It's really exciting to see so many people in the room. I'm going to talk about data-centric metaprogramming. My name is Vlad Ureche. On screen you have my coordinates in case you... I'm a software engineer at Cyberhaven, and I just graduated from EPFL. And my main project is Scala mini-boxing. What I'm going to talk to you about today was originally part of the mini-boxing project, but then seeing its potential, I tried to push it to a different project separate. During the presentation, I will be giving some technical details. Please do stop me if what I explain is not very clear to you. We have plenty of time, so please directly ask. So first we're going to look at motivation. And motivation comes from the object composition. Namely, if you take the vector class in the Scala library and you have your very own defined employee class, for example, maybe it corresponds to a table row, you will compose these two and get a vector of employee. So far, so good. What is bad about this is that if you're traversing this vector, you will be dereferencing a pointer each time you're visiting an element. And this can be very harmful for performance. Of course, there is a better way to represent the data without having each employee as a different object. We could take a column-oriented storage, and this would mean that we put the IDs one after the others, and so on. This is very good because it gives us performance and makes a much better use of the heap. We use less memory and put less pressure on the GC. Okay, so we see the problem now, right? We have object composition, it's great, but it leads to suboptimal data structures. If we look at a vector of T, it is unaware of the employee class we defined. So that makes it suboptimal. The way it stores data is suboptimal. And this is not really limited to vector. It's actually a problem that affects all generics, and it also affects all the collections. And it also affects functions, we'll see later. And most people here in the room, I assume you already know better representations for your data, but you can't just manually go in a code base and start changing every vector of employee by something else. It's too much work and it's not maintainable. So as a compiler hacker, I think that the compiler should do that for you. And I'll try to convince you why. But before that, you might think, okay, we've heard so much about optimizers in this edition of Scala Days. We've heard about the Scala.js optimizer. We've heard about the Dotty linker. We've heard about Scala native. So why do we need something more? All these optimizers do a great job, but they're bound to one constraint. They have to respect the semantics. So no change they do can affect any of the possible corner cases that you have for a certain statement or for a certain expression. So that means they have to be pretty conservative in what they do. Now, you as programmers have full control over your code base. That means you know what is accessed, when it is accessed, and how it is accessed. And that lets you break semantics just enough to speculate that about what will happen to your data. And that will let you have better data representations. Okay, so the current challenge is you have no way, knowing a better data representation is not enough. You don't have a way to communicate that to the compiler. So we're basically in a situation where we're stuck with either safe code or fast code. And this is where my project comes in. Data-centric Metaprogramming is a Scala compiler plugin that lets you tune the way you represent data in your program. This website is Scala ILDL. you can read about it and see more and try it out. Now let's talk about the transformation for a moment. And the transformation, when you're transforming data representation, there are actually two steps involved. First part is coming up with a definition for the transformation, coming up with the better data structure. And this is fundamentally something you as a programmer only know how to do, because it's based on a speculation, it's based on knowing how the data is accessed, and very interestingly, it's a one-time effort. So once you defined the better data representation, this is all the effort it takes. So I think this is the part that should be done by the programmer. And this a compiler will never do for you. And then there's the application part, which is the repetitive and tedious part of just going into the code and modifying it such that it uses the better data representation. And this is pretty annoying, because if you want to have a high-level code base that is easily maintainable, going into the source code and modifying data representation is something you won't want to do. It's better to leave it to the compiler. So let's focus on the definition part. Let me show you. Yes, did I see a question back there? Okay, so let's look at a definition. How could we define such a transformation? Here's the example, here's the transformation for the example I gave you earlier. And what you see here is the two types, the target and the result, what we're changing. Then we tell the compiler, whenever you need to change values of one type to the other, here's how to do it. And finally, we tell the compiler how to run methods on the vector of employee on the new representation. This is a shortcut, because it could transform them back to a vector of employee and run the method on that representation, but it's not very interesting. You want to execute directly on the new representation. This is all there is to defining a transformation. And then the application part is all in the hands of the compiler. I won't go into the details of how this works. There's a paper on it, and it's pretty long and pretty tedious on how it works. But I'm more interested in showing you some challenges that we faced during the development, and that will give you an idea of how this whole thing works. And the first challenge is open world. Let's see what this is about. So let's look at this scenario. We have a vector, we have the employee class, we have the vector of employee throughout our code, and suddenly one of the developers says, all right, I'll change it to a better representation. All good and well until somebody comes up with a new employee or a subclass of the employee, which adds a department field. So what happens then? Well, oops, it's not really meant to happen. And this is the open world assumption. Globally, anything can happen. You could subclass vector, you could subclass employee, or the vector behavior might change. What I would say is, locally, in a code base, you as the programmer have full control. You know the employee class, you can make it final, or you can say whenever something gets into that list, if it's not an employee class, if it's something else, we reject it. And you can also limit the code transformation to that code which suits your speculation. So that parts of the code, the parts of the code that fulfill the invariance you wanted. So how can you do that? The answer is using scopes. What is a scope? Let's look at this method. It's indexing the salary of everybody in a company. You will probably recognize the syntax. If you wrap this scope transform with the transformation we just defined around this method, suddenly it will be running on the new representation. So the interfaces remain the same, the colors don't need to be changed by you, they're changed by the compiler, and suddenly this will be faster. Now, okay, so this I said. So scopes can wrap statements, can wrap pretty much anything in your code, and it's inlined immediately after the parser. And definitions inside the scope are visible outside. And before you ask, it's not a macro. Unfortunately, you couldn't do that with the macro. So transform is a special marker that the compiler with the plugin recognizes. Okay, so what do we use scopes for? We mark locally closed parts of the code that we know can be transformed. And values incoming and outgoing from this scope go through our own conversions, the conversions that we wrote specifically. And this lets us reject unexpected values. So if some new programmer doesn't know about the rules, this will stop them. And now let's look at another challenge, namely the fact that we have, let me not give you I won't give you the key here. Tell me, what is the best representation for a vector of employee? Who thinks they know? Nobody? Really, nobody knows the best? Okay, thank you. Yes, that is the answer. Because it depends, right? It depends on the case. If you're going to iterate through the vector of employee, you're better off with a column-oriented storage. If you're working in memory with the data, you will probably want some very, very compact binary representation. Finally, if you're communicating with a JSON server or an XML server, you will want to store that data in the particular format you're going to use to communicate. So it really depends what is on your use case, what is the best representation for your data. And the scopes allow us to mix the representations. For example, we've seen here the index salary method transformed with a column-oriented storage. Now, if we just change the transformation we use for that scope, suddenly we're working on a compact binary representation or on a JSON-based representation. So it's as easy as it gets to change certain parts of the code to different representations. Which brings us to the next topic. How do you compose parts of the code that use different transformations? For example, here I have a method that indexes all the salaries by 1%. And it's calling the index salary method, which is transformed. So here we have a call from some code that has not been transformed to some code that has been transformed. So we have original code and transformed code. And how do we handle calls between them? It actually happens that we have an entire array of cases to cover, original code or transformed code, calling all these cases. And I'm going to show you what happens in some of these cases. So for example, if we have original code, calling original code, that's easy. We don't need to do anything. Nothing is transformed. What about the cases where some original code calls transformed code, or vice versa? Well, the compiler automatically figures this and introduces conversions at the right places. For example, we could switch from the column-oriented storage to the row-oriented storage we had before, or back, as necessary. Now, another question is, what happens if you have the vector of employee in JSON format and you suddenly want to transform it to something else, to a binary blob, let's say? This is a hard question, and it involves transforming twice or having an optimized transformation conversion between the two. And maybe the hardest case that we have is what happens when you have transformed code that, oh, I'm sorry, I've No, so if you have the same transformation, we don't have to introduce any conversions. And that works even across separate compilation, which is a very difficult thing because what happens is one compilation run has to be aware of all the transformations that happened in the other compilation runs. And finally, with a different transformation that I already told you, you have to go twice. So these are all conversions that you have to do automatically that the compiler does automatically for you. And if you think so far is very complicated and there are many cases, think about overriding as well. This introduces a new set of challenges. Let's take, for example, this printer class that takes a vector of t and just prints the elements to the screen. And let's define this employee printer, which extends printer of employee. The print method in the class implements the one in the trait. If we were to wrap this class in a scope, the signature for method print would no longer implement the one from the trait. So this is a big problem. This is something that if you were to rewrite code on your own, you would have to go in and define the second method. The good thing is, all these things are taken care for you by the compiler. So once you've defined the data representation transformation, everything else is automated. Now let's look at some applications to see exactly how we can use this. For example, we've shown column-oriented storage. That's one case. And in some benchmarks, we got up to 5x speed up by deploying this transformation. Or, for example, we can retrofit the value class status like you have in, for example, in Scala native Anstract. We can have this on classes in Scala. For example, a tuple, the tuple in Scala is specialized, but it's not a value class. So it has to be allocated on the heap. Well, we can transform that and we can make it allocated on the stack. And this is pretty ridiculous. It gets 14x faster if we do that in benchmarks. So it's very important to use the best data representation for your task. Another example is deforestation. So probably some of you have code like this in your code bases. So you have a list or some collection, you map once and then you map another function to it. And after each map, what happens is that the program computes an intermediate list. And after adding 1, it computes a new list. After multiplying by 2, it computes a new list. And finally, when you call sum, it gives you the final result. So this is not really great because we could get rid of the intermediate lists if we know the functions don't have any side effects. Because, for example, if we had print here and here, it wouldn't be correct to get rid of the lists. So we can, if we know, for example, as programmers that our functions are pure, we can just wrap the code in a transformation that does deforestation. And what will happen is each map will accumulate the function, and these will only be executed, the functions will only be executed when we compute the final result, so the sum. And this is 6 times faster. You could go to arbitrary speedups. In this case, just put more maps or more filters, and you get more benefits. I also told you about functions. So I talked about collections so far and containers, but let's look also at functions. I wanted to make sure you know that this is research, so it might not make it into a product, but you can play with it nevertheless. This is something on Spark that I did. And just to make sure everyone is on the same page, I'm going to show you a bit about RDDs, reliable distributed data sets. This is one of the key abstractions in Spark. And an RDD can actually have be in two situations. It can have primary data, which is, for example, data coming from a CSV file, or can be derived from another RDD, which is, for example, by mapping a function. And if we look at closer how mapping works, it's usually a function, a programmer gives a function that takes an object X and returns an object Y. But in fact, it's more complicated because the primary data is encoded in some format. It's serialized. So before running this function, we actually need to take the encoded data, decode it to produce the object X. And after running the function, executing and producing object Y, we actually need to encode it back, to serialize it back down to some representation, some encoded representation. This is not great because we need to allocate two objects that we could get rid of. Okay, so how could we get rid of these objects? Well, if we had a modified version of the user function, it could operate directly on the encoded data and output encoded data. Of course, it's nowhere near as simple as it looks, and I'm going to show you some challenges that I faced when trying this out. So in some cases, the transformation is not possible. You could imagine calling outside methods like Java methods or Java calling JNI, calling C code. That we cannot transform. So what we do in those cases, we issue compiler warnings. We let the programmers know that a method is not possible or a function is not possible to transform, and we give them the exact reason this is not possible to transform it. Fine. Also, we suggest how to fix the problem. Enclose the other method that is not transformed in a scope, or if it's outside, if it's, for example, Java, it's not possible to do it. Express it in Scala. And this is all reusing the machinery in the mini-boxing plugin. So there's something, it's not something new. It's just reusing what exists already. Okay, so internal API, Spark uses iterators everywhere. So iterators require materializing values. I had to replace them by pretty complex buffers. And it took some extensive refactoring and rewriting. The prototype I developed, I would actually call it a hack rather than a prototype. It's a modified version of the Spark core, and the RDD, the representation, data representation in the RDD is configurable. It's quite limited because you can only use map, filter, and flat map that are optimized. It's not the full set of the full API that is getting transformed right now, mainly because I didn't want to modify all the code. But, and there are large parts of the automation that still need to be done. But if we take this example of parallelizing a collection, mapping, filtering, and then collecting it, it automatically does deforestation. But we can further squeeze about 45% speed up by tuning the data representation in the RDDs and the functions. So more details on this, for more details on this, watch the Spark Summit talk I gave a while ago. Okay, so let's conclude. I'm going to finish earlier, so we have plenty of time for questions. We saw that object-oriented composition gives us inefficient representations. And one of the solutions we have is data-centric metaprogramming that lets us give the best use, the best representation for our data. And everything else is automated by the compiler. Questions, is it possible? Yes, definitely. Is it easy? No, not really. It's pretty complicated what happens in the compiler. And I would like to ask you whether it's worth it and whether you would find use cases for this in your projects. With this, I thank you, and for more information, visit the website. Thank you. I see a question there.
Yes, you talked about this object-oriented representation is inefficient. I wonder, has that always been the case, or is that sort of something that is caused by the sort of modern CPU design with a lot of caches and stuff? Or was it the same sort of 25 years ago?
So 25 years ago, we didn't have that much flexibility. All of the inefficiency in data representations that we use today comes from the fact that languages offer us the flexibility. So what do I mean by flexibility? For example, you can evolve the vector implementation. You can subclass vector, you can subclass employee, and all of these are independent of each other, and they still are able to interoperate. If you think of a better representation, it usually has to fix something. It has to say, all right, employee doesn't evolve from now on, or vector doesn't evolve, or neither of them evolves. So this is, I wouldn't say it's a bad thing, what we have now. I would say that it's just something that we pay for the flexibility in terms of performance. Did I answer your question, or?
Well, not really, maybe.
Can you rephrase it?
Okay, so my theory is that this performance boost that you get by this perhaps object decomposition, that you wouldn't have gotten that sort of on a sort of Intel 386 sort of 20 years ago, but you will get it on a modern CPU.
Okay, I see. So something that, when you mean that something relies on the cache, for example. Yes, it is one of the optimizations you can have relying on the cache. It's not necessarily tied to the techniques here, because you can do other optimizations that don't rely necessarily on the cache or on some features of the processor. But generally speaking, yes, you do some speculation where you say, I think if I structure my data in this way, the processor is going to execute faster. So yes, it is related in that sense to modern architectures, processor architectures. Yes?
Yes, so I had two questions. First one is when bypassing methods, like you showed in the example, if I don't bypass a method, will there be a conversion if I use that method within one of the scopes?
So what happens if you don't have a bypass method? First of all, you get a warning that tells you, hey, this is suboptimal. And the compiler automatically converts to the original representation, which can be very expensive,
right,
and invokes the method. This is something that is done to have some version of the code that is still valid during compilation. And of course, you'll know.
Yeah, so my second question is, because the actual conversion, the initial conversion in your example, vector of employee to employee vector, that would require going through the whole vector. So where are the performance sort of, is it more performant to do that? I suppose you have to have something that does multiple iterations over the vector for it to actually be more performant. Do you have some kind of cutoff where it starts paying off?
That's a very good question. In the benchmarks, what I did was to build up the data structure from scratch, element by element, in which case you build it up directly in the optimized representation. But I can imagine in some cases the cost of conversions would be greater than the cost of the gains that you get. And I think this is ultimately something that only you as a programmer will be able to benchmark on a case-by-case basis and decide whether an optimization is actually an optimization or a de-optimization, and it hurts performance. So this is why the message I'm trying to send is, I put the power in your hands. It's up to you how you use it and how you transform the data. The compiler does the tedious hard work. Yes, so I see 2 questions.
I have on the comment about the architectures. I think actually the ways we use the architectures are actually worse in some scenarios, especially for certain cases. Like if you have the vector of all the arrays I'm iterating through in the same cache lines, I will get better performance, no matter what version of the hardware, 386 or the modern one, will also happen. There's actually a talk by the guy from, I forgot his name, Martin Thompson, on how small changes to the way you navigate through memory will do massive impacts on the performance you have. So in general, just good strategies will improve. The question I have is, in your experiences, have you been trying to see, for example, if I start doing a bunch of transformation, I might lose information, especially in the data-rich context, might be hard to check. So is there a way to do this? Should I try small and then scale up, or how do I approach this practically as I put more and more transformations?
Yes, thank you for that question. That's a tough one. So I wouldn't know how to. You can start small, of course, and see how it scales up. If it scales in all cases, if you have, usually what will happen in my experience, what developing these transformations is, I get guided by the compiler. The compiler starts telling me, hey, you need to also add this bypass method, or you have a double conversion here. Could you please add a direct conversion between these two? And as I add more code to the code base I transform, I constantly get these warnings that basically tell me what is the next step that needs to be done. I don't know if I answer your question entirely, because I don't have the experience of a huge code base. Even the Spark core, the part that I modified, I still consider it rather small. It's in the order of, let's say, K lines of code. So it's not huge in the sense of tens of thousands of lines.
So there was a talk yesterday about the Dotty linker, and it also allows rewriting of code. What's the relationship between these two solutions?
So I guess So the main difference, the way I perceive it right now, is in the Dotty linker you have more syntactic rules for transforming the code, such as, for example, if you have 2 maps, one happening one after the other, you rewrite that to a single map. But the focus is on transforming code, transforming the code itself. Of course, you can constrain the types of those expressions involved. On the other hand, what I present here is focused on the data. So you want to transform not the code. The code is a secondary concern. The main point is to transform the way data is represented. So the rewrite rules, as far as I know, will not transform the inner data representation. Will only transform the code to make it more efficient outside. Did I answer your question?
Can you put a bit more light on why this dereferencing in case of employee is slow? So basically, what the resource suffering more? Is it CPU cycles, or like why is it slow?
Okay, so it depends a lot on the case. So in some cases you're CPU bound, in other cases you're memory bound, in other cases you're IO bound. But the typical problem that this solution will resolve is memory-bound operations. So things that you do in memory, but you do so inefficiently that you could do much better if you didn't if you used a different way to structure the data.
Okay, thank you.
See one question there.
Yes, maybe this was answered during the talk, but before this, there was a talk from Eugene about Scala Meta. Would this, like, how does metaprogramming relate to this? For me, looking from the outside, it seems that you could do a lot of the same things, but are there any sort of restrictions or limitations when comparing?
So metaprogramming is a very broad topic, and especially the way Eugene sees it, it means changing anything in your program in any way possible. And to some extent, I feel that constraining it a little bit and focusing it on a specific topic can give you more tangible results, such as this data-centric metaprogramming. It's aimed at a single use case, data representation. It's much more limited, but on the other hand, it doesn't have all the complexity that you would have in writing a macro, for example, that transforms the code in such a way that would get you the same benefits.
Okay, thank you.
Have you seen any positive impact on the garbage collection?
Commenting on the garbage collection, I don't have so much experience with problems related to garbage collection, but what I can say is every time you lower the heap footprint, you're less likely to run into GC problems. And that's a trade-off. I mean, most of these transformations are probably going to get rid of some alignment, some object headers, which will reduce the memory footprint. Of course, you could write a data transformation that gives you better speed up at the trade-off of using more memory, in which case you might be running into some GC trouble. Did I answer your question?
Yeah. Yes, thank you.
Thank you. Okay. One more question there.
I'm wondering about this object decompositioning and this column-oriented way of storing them. When you have strings, are you then sort of concatenating all the strings in a single object or in some way? Or?
So this has been an ongoing discussion that the Java architects have been thinking a lot about. What is the best way to merge strings lazily or eagerly? And it's really down to each case what is the best thing to do. What I can say is you start off with strings, and using a data representation transformation, you can go either way. You can eagerly merge strings, concatenate strings, or you can make it lazily. It's up to you. It gives you as the programmer the power to choose. What is the best way depends a lot on your program. Okay, so I don't see any more questions. Thank you all for being here, and hope to hear from you.